Welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, which is in England. And in this video I wanted to have a look at the unusual profile in the spectrum of some stars. So these are P Cygni stars and they give this P Cygni profile, and it relates to some of the largest stars in the universe, luminous blue variable stars. And what I want to do is cover why we get this profile and what it means for the star. So even if we can't actually image the star, it tells us a lot about that particular star and the environment around it as well. So first thing, before we actually get this profile, is we need to get the spectrum of a star. So the spectrum of a star is the amount of energy that is emitted at each wavelength. So here you've got it in the visible part of the spectrum. You've got a blue star, yellow star, red star, and it relates to the temperature of the star actually. And I'll mention in a little while how you can actually get the temperature of the star just by getting the spectrum. So the amount of energy that's emitted per wavelength, and you get that plot, you can then actually calculate the temperature of that star from that. So to do that, what you actually need is a spectrometer. So what you would do here is you would actually take a telescope, and instead of taking an image of the star, you want to split the light and get the spectrum instead. So what you can do here is you would put the spectrometer on, which is in professional telescopes, so that some of the large telescopes around the world, they don't use a grating or a prism, they'll use both, which is called a grism, and that allows the light to be split, and it will then essentially project it onto a detector, and you get the image of the spectrum instead of the image of the star. And you can actually do this on your own telescope at home. You can actually make a fairly cheap and easy spectrometer to put on, which will split the light, and then you can do that yourself. So what do you actually get if you then to plot that? So on the left hand side there you've got the spectrum. You can see lots of black lines and that, but ignore the black lines for now. If you were to plot that against the wavelength, you'd get something like on the right, which is the spectrum of the star, and depending on the temperature of the star, it will have a slightly different shape. It will be more over to the left or more over to the right because it's temperature dependent. That image of the spectrum will have some pixel value, and you're just plotting that pixel value against the position along the spectrum. You would calibrate it to a particular wavelength, so you normally use a calibration lamp, but anyway, you get this spectrum, which is what we want. So the peak wavelength relates to the temperature. So you can see here that the green line, which is a green star, has a temperature of 5,500 Kelvin. That's peaking around about 500 nanometers. So it's basically peaking towards the shorter wavelength, which is obviously higher energy. The ones, or the redder ones, cooler down, are 3,500 Kelvin, and that's peaking more towards like 800 nanometers. So basically, depending on where the maximum peak of that line is, will tell you the actual temperature of the star. So we can use Wien's law to do that basically. So if we take, for example, the green one, we would say here that actually the peak wavelength, which is the left-hand side of the equation there, is 500 nanometers. You put that in, you've then got your constant of proportionality at the top. Well, you'd rearrange for temperature first actually, but then you can get the temperature, and it should come in around about 5,500 Kelvin, something like that. I'm only approximately kind of guessing looking at this plot here, but that's how we get the temperature of a star, by taking the spectrum, looking for the peak wavelength, and assuming it's a black body as well. So what do we mean by a black body? Well, stars are considered ideal black bodies. So they're in thermal equilibrium, and they would have the following two characteristics. So if it's an ideal emitter, it's going to emit at every frequency, and it will radiate energy at a similar rate or equal to any other body of the same temperature. Basically, if you've got two objects at the same sort of temperature and they're both ideal black bodies, you'd get the same sort of spectrum, essentially. It also means that the energy is emitted isotropically. So if you were anywhere around the star, so if you were behind the star, to the side, it should get the same sort of measurement really. So it's not really dependent on where you're measuring from. It should be equally emitted all the way around essentially. So that's the general black body like spectrum of a star, but the thing we're interested in for these P Cygni profiles is the absorption and emission lines, which are kind of smaller features on the main spectrum basically. And if you have a look at the top here, you can see some black lines in there. And actually, if you draw that, plot that spectrum, so it's got the brightness or the energy as a function of the wavelength, you can see you've got dips in brightness. So actually there are locations in that spectrum where there's less energy. Now that's where energy is being absorbed by certain elements, molecules, things like that. In a star, it's mostly going to be hydrogen because the outer layers are predominantly hydrogen, in a main sequence star at least. And the outer layers are cooler. The energy is not made all in the star, it's made in the central part. That energy then has to make its way out to then be emitted as light. That means the outer layers are going to be cooler, and they can absorb some energy at specific frequencies or wavelengths which relate to hydrogen. And most of stars will have these features of hydrogen because of their outer layers, really, which are cooler and absorbing at that particular wavelength. Now, some stars have an unusual feature, which is emission lines. It's quite unusual for a star to have that. But what it means is you've got some ionized gas around the star, which is emitting at its own wavelength. So that's not the star. The star creates the main spectrum, but it means you've got some of this hot gas around the outside instead. Now, some examples, I suppose, of that is if you've got a very large star that has lost its outer layers, that star is very hot. It's then basically heated up that gas, it's ionized, the gas itself is then emitting at its own wavelength. We can detect that in the spectrum. Same again if there's any nebula around which is emitting at its own wavelength, we can pick that up, and you'll get a very specific sharp line because let's say it's going to be hydrogen or something like that. That will emit at a very specific wavelength, as opposed to it's not going to behave like a black body because it's not like that. So an ionized gas, you get these very strong lines. So the P Cygni stars then. So it's named after the first star that was found in Cygnus constellation. This is a luminous blue variable star, and the P Cygni profile is pretty much constrained to these sorts of stars because they have something going off with them which is unique to them, which gives you this unusual profile. So originally named from this star in the Cygnus constellation. And this is what it looks like. So now we actually have a combination of an absorption line and an emission line in the spectrum of the same line, which sounds a bit bizarre. So it's this hydrogen line. So this one in particular is the H alpha line, so emitted from the hydrogen alpha. Basically that one. And it's being absorbed and it's being emitted at the same line, which is a bit unusual. So why might it be doing that? So what we're actually detecting then, if we look at the absorption line, we're getting a blue shifted absorption line. So if we're looking at the star, it means that there's some gas between us, or I should say some hydrogen actually, between us and the star, which is moving very fast towards us. So it is blue shifted. So Doppler shifted towards us means it's blue shifted. So actually it's absorbing that wavelength, but it's moving towards us, so it's moved slightly towards the shorter wavelength. The other part is redshifted. So if there's gas behind the star, which is emitting at its own wavelength, so that is ionized and it's basically emitting some energy, we get a redshifted emission line from that. So again, because it's traveling away from us, it gets redshifted. So now we have the same gas basically, but some of it is moving away from us and some of it is moving towards us. So we get a combination of this in the same feature. Now, what does that tell us about the actual star? Well, it tells us that these P Cygni stars, this P Cygni profile, any star that has that, it's got a rapidly expanding hot shell of gas because we're detecting some of it that's traveling away from us, some of it that's traveling towards us. We can't really detect it if it's traveling perpendicular because if you think about the Doppler effect, it's not moving relative or line of sight to us. So we're getting the bit that's moving away from us and the bit that's traveling toward us. And it tells us there's a hot expanding shell of gas around this particular star. Because they're so large, they actually can begin to lose their outer layers. They're so luminous that they can actually lift their outer layers out of their own gravitational well, basically. So thank you for watching, and if you enjoy, then do check out some of the other videos.